Hey everyone, and welcome. Today, we're going to dive into the heart of abstract algebra and untangle two concepts that sound almost identical but tell totally different stories, the center and the centralizer. And I promise you, by the end of this, you'll see it has way more to do with the social dynamics of a party than it does with scary equations.
So let's just forget about math for a minute. Seriously, picture this. You're at a big, bustling party. You've got all kinds of people here. They're mingling, they're chatting, they're making connections. This whole scene, that's our stand-in for a mathematical group. It's just a collection of things that interact with each other in some really interesting ways.
Now, at any party, you've got those social butterflies, right? The people who are the life of the party. They can talk to anybody about anything. They just get along with everyone. But then you also have the quiet types, the ones who might stick to the corner but have a really deep, special connection with one particular person. This exact distinction between getting along with everyone versus having a special connection, that is the key to everything we're talking about today.
Okay, time to bring the math back into it. At what we're going to call our commutativity party, the idea of getting along is what mathematicians call commuting. It's really all about how these different elements interact with each other.
So what does commuting actually mean? It's simple. It just means the order you do things in doesn't change the result. If you combine element A with element B, you get the exact same thing as combining B with A. They commute. It's kind of like having a great conversation. It doesn't matter who speaks first, the point gets across just the same.
All right, it's time to meet our first guest of honor at this party, the center. These are the ultimate social butterflies. These are the elements that are friendly with absolutely everyone at the party, no exceptions.
Now, I know the formal definition can look a little intense, but don't let the symbols fool you. It's just a mathy way of saying what we already know from the party. The center, which we call Z of G, is just the collection of elements, we'll call them Z, that commute with every single other element G in the whole group, period.
So let's break this down. The vibe here is universal. These elements get along with everybody. That means the scope is global. It's not about one-on-one friendships, it's about how they relate to the entire group. And here's the cool part. If you happen to have a group where everybody commutes with everybody else, that's called an abelian group. Then guess what? The center is the entire group. The whole party is just one big, happy, communicative family.
So now that we've met the universal charmers, let's shift our focus to a much more, well, focused kind of relationship. This brings us to our second guest, the centralizer. And this one is all about those special one-on-one connections.
See the difference? The centralizer of a specific element A, which we write as C of A, is the set of all the other elements, G, that commute with just that one specific element A. We don't care if G gets along with anyone else, we only care about its relationship with A. So you can see the vibe here is specialized, and the scope is totally local. It's like we're putting one specific element under a microscope to see who its friends are. And here's a neat little fact. An element A is always in its own centralizer. Which makes sense, right? A always commutes with itself. You always get along with yourself.
Okay, so we have the center, the life of the party, and we have the centralizer, the close friend. Now let's put them side by side to really see how they stack up. This table just lays it all out so perfectly. Who does it commute with? The center gets along with everyone. The centralizer? Just that one element, A. And how many are there? There's only one center for the entire group, but you have a different centralizer for every single element. Their goals are different too. The center finds the most universally friendly part of the group, while the centralizer just finds the buddies of A.
So how do these two ideas actually relate to each other? Well, this is where it gets really elegant. There's a simple but really powerful rule at play. The center, Z of G, is always a subset of any centralizer, C of A. It's like they're nested inside each other. And let's bring that right back to our party. It's actually just common sense. If you're one of those people who gets along with everybody in the room, meaning you're in the center, then by definition, you must also be friendly with that one specific person, A. So you're in their centralizer too. It just has to be true.
All right, let's step away from the party for a second and see how this all plays out in a real mathematical context where order is a huge deal, multiplying matrices. You know, matrices are a perfect example of a group that's usually not commutative, which makes them a really fascinating place to look for the center and the centralizer.
Yeah, in the world of matrices, A times B is almost never the same as B times A. And because of that, the center, The set of matrices that get along with all the others is incredibly small. It's a super exclusive club, basically just multiples of the identity matrix. But if you pick one specific matrix, let's call it M, you can absolutely find a whole set of other matrices that do commute with it. And that set, that's its centralizer, C of M.
So why does any of this matter? Why is this distinction so important? Well, it's because the center and the centralizer are like tools that help us understand the deep, hidden structure of a group. They give us a way to measure its friendliness, its level of commutativity at both a huge global level and a tiny local level. It's all about revealing the symmetries hiding inside.
And really, that's the key takeaway right here. The centralizer is the tool you use when you want to find the universally compatible core of a system. The centralizer is what you use when you want to zoom in and find all the elements that are compatible with just one single piece. One gives you the bird's eye view, the other gives you the microscopic view. Ultimately, this is so much bigger than just algebra. This is about a fundamental pattern of interaction that you can see all around you. And it really makes you wonder, right? What other hidden rules of universal versus specific compatibility are shaping our world right now, from the way social networks form to the bizarre behavior of particles in quantum physics? Thanks for joining me on this one.